This is the graph of log base 10 of x. And if you notice, we have a vertical asymptote at x equals 0. So that's where I say vertical asymptote is x equals 0. So that means that the graph, as it gets closer and closer to 0, as x gets closer and closer to 0, the y values are getting closer and closer to negative infinity. So we know as the x values approach 0, the y values are approaching negative infinity. And then as the x values approach positive infinity, the y values are also approaching positive infinity. So this graph just keeps growing and getting larger and larger. But if you notice, in this area between 0 and 1, so right in here, in this area between 0 and 1, the y values are shooting up from negative infinity up to this x-intercept. The x-intercept is at 1, 0. So there's my x-intercept. So now let's think about what the domain and the range are of this function. The domain is going to be all x values greater than 0, and the range is all real numbers because you can have anything from negative infinity to positive infinity. So you could write that in interval notation as going from negative infinity to positive infinity. Exponential functions and log functions are inverses, which means if you take an exponential equation and reflect it over the line y equals x, you will get the log of log base 10 of x. So if I've got y equals 10 to the x, log base 10 of x is the inverse. And as we learned earlier about functions that are inverses, they have points with the coordinates reversed or flipped. So on 10 to the x, I have the point 1, 10. Then on log base 10 of x, I'm going to have the point 10, 1. On the exponential graph, I have 0, 1. On the log graph, I'm going to have 1, 0. And on the exponential graph, if I have negative 1, 0.1, I'm going to have 0.1, negative 1 on the log graph. And the domains and ranges are going to be flipped. So on an exponential graph, 10 to the x, the domain of 10 to the x is all real numbers, which means that the range of log base 10 of x is going to be all real numbers. The range of an exponential function is y greater than 0 because we have a horizontal asymptote. I'm going to write, we've got a horizontal asymptote at y equals 0. So for the log of x, we are going to have a domain of x greater than 0 because we have a vertical asymptote at x equals 0. The intercept on our exponential graph is 0, 1, which means, and that's a y-intercept, and which means that we have an x-intercept on the log graph at 1, 0. So we have two graphs that are inverses right here. The first one is 2 to the x minus 3, and then I use properties of logarithms to find the equation of the inverse graph. In fact, I think we did this in an earlier, we did this in 5.1c. So the domain of 2 to the x minus 3 is going to be all real numbers, which means the range of my log graph is going to be all real numbers. The range of my exponential graph is, it hasn't shifted up or down, so it's only shifted side to side. So my range is going to be y is greater than 0, which means I have a horizontal asymptote at y equals 0. The domain of the log graph is going to be x is greater than 0, which means I have a vertical asymptote at x equals 0. And now let's see if we can find the intercepts. The intercept for the exponential graph, if I plug in 0, I am going to have 2 to the negative third, which is 1/8. So my intercept is 0, 1/8. And on the log graph, that means that my intercept, the exponential was a y-intercept. The log graph is going to be an x-intercept. The x-intercept on my log graph is going to be at 1/8, 0. We flip-flop them. So let's sketch a log graph. Basically, if I know the graph of y equals 2 to the x, I can just flip-flop the points and get my log graph. So I'm going to actually figure out the points of the 2 to the x graph, because this is base 2. So if I plug in a 0 for x, 2 to the 0 is 1, which means on the log graph I have 1, 0. If I plug in 1, I get 2. So on the log graph, I'm going to have 2, 1. I wrote right over, trying to erase. I wrote right over the point, 2, 1. Then if I put in 2, I get 4, so I have the point 4, 2. If I put in 3, I get 8, so I have the point 8, 3. I know that this graph hasn't shifted side to side at all, so I've got my vertical asymptote right here, and you should draw it and label it. Vertical asymptote, x equals 0. So I know this graph is getting closer and closer to the vertical asymptote, and it's going like this. So if you get the points of the exponential graph, you can flip-flop the coordinates and know the points on the log graph. 1, 0, 2, 1, 4, 2, and 8, 3. Let's do another one. So here what we do is we could take the points that we had from the last graph and multiply them by -2. The negative will flip the log graph upside down, and the 2 will stretch the graph further away from the x-axis. But I'm going to take those points that I had from the last slide, which were 1, 0, 2, 1, 4, 2, 8, 3, and I'm going to multiply the y values by -2. So multiply y values by -2. So now I'm going to have the point, I'm still going to have a 1, 0. I'm going to have a 2, -2. I'm going to have a 4, -4, and an 8, -6. I have not shifted side to side, so I have my vertical asymptote still here at x equals 0. And now the graph is flipped upside down from what a log graph normally looks like. And that's my graph right there. The last thing on this lesson is to perform a logarithmic regression. Now, the one thing that you need to know about logarithmic regressions is that you're actually not going to be looking for the word log when you go to stat calc. So remember, you press the stat button and then you see this calc menu right here. There's not going to be something called a log regression. What you're instead going to be doing is called an LN regression. LN, just so that you know, is log base E. And E is not something that we taught you this year. But just know that E is kind of like pi. Like pi is 3.14 dot, 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 dot. E is a number that appears in a lot of financial calculations, and it is, I believe it's 2.71 something, something, something. So just know that you're going to be doing a regression in a base E. That's all you need to know. So it's ln for natural log. It's called the natural log. You'll learn more about the natural log next year in pre-calculus. So when we perform a regression analysis using natural log, we are going to be trying to identify an A value, which is the shift up or down. And we're going to be finding a coefficient in front of the natural log of x. So these are the two values that the regression are going to give you. They're going to give you an A value and a B value. And that's the equation that you need to write is y equals A plus B natural log of x. So as an example, we have this table of data, which is life expectancy. So the table to the left shows the average life expectancy in years from 1900 to 2010. So the row one with the 1 here is the year 1900. And the row with the 2 is the year 1910. So it's every 10 years since 1900. 11 represents 2010. So this is 1920, 1930, 1940, 1950, 1960, 1970, 1980, 1990. Nope, this is an error. This should be x equals 12. I knew it. That's why I started counting, because I had a feeling something was off here. So 11 is the year 2000. And 12 is 2010. There we go. So we're going to use logarithmic regression to fit a model to this data. If you're putting this table into Desmos, this is what you're going to type. First type in the table, and then type y sub 1 with a little tilde sign, and then a plus b times natural log, or ln, of x sub 1. So I'm going to do it in my calculator. I'll be back in 1 second. So I did the regression, and my a value is 42.5272. I'm going to round to 4 decimal places, plus my b value, which is 13.8575, and that's going to be times the natural log of x. So there's my equation. And now I'm going to use that model to predict the American life expectancy for the year 2030. So the year 2030 is going to be 2020 is 13, and 2030 would be 14. So I'm going to plug 14 into that equation. In your calculator, you're going to want to do the natural log of 14. So natural log is a button right below your log. Natural log of 14 is 2.6390. I'm going to multiply that by 13.8575. and add that to 42.5272. And I get 79.0979. So in 2030, I predict that the life expectancy, the average life expectancy, would be 79.1 years. I'll write 79.1 years. And there is a regression problem for you to practice as homework, so get to it.